So, in this lecture, we will talk about a different mechanism by which the materials can fail, and that is known as fatigue. So, the end of this kind of deformation will be ultimately failure. But the phenomena we have to understand. So I'm not writing fatigue failure, but I'm writing just fatigue, so that we talk about fatigue without focusing too much on the failure. But the reason why we are studying is because components usually fail due to this kind of deformation. What happens is that fatigue failures, so the failure which happens because of this kind of behavior is usually subtle. So you wouldn't know if the material is getting damaged, and the triggers usually for this kind of damage are unavoidable. So in order to understand this more, we need to first understand what it is, and then we will talk about why it is important. So fatigue, basically, if in it the meaning of the word usually in English is taken as tiredness, exhaustness of the material or of the human body or of anything. So, but in technical terms, when we are talking about mechanical behavior of materials, this has a specific meaning. So a material probably can get exhausted in monotonic loading or by some other means of loading, or maybe not, but in mechanical behavior of testing, fatigue usually refers to cyclic loading. So there has to be application of load, and it cannot be constant. It has to increase and decrease in a cyclic way. And this cycle can be a very smooth cycle, or it can be a very haphazard kind of cyclic loading. And depending upon that, the material performance will also depend. So when something fails under fatigue, usually you see certain lines, and these lines, they look like this. These are called beach marks because they look like the lines which forms on the beach. So they're called beach marks. But beach mark is evidence that the material has failed under fatigue loading, but the absence of beach mark does not mean that the material has not failed under fatigue loading. So even if you don't have beach marks, the material might have undergone fatigue limit. So beach marks are visible from the naked eye. So it is a macroscopic feature. Okay, so a broken sample under fatigue loading, you can see this on a low magnification microscope, or even from the naked eye you can see this feature. More evident or signature of fatigue fracture is visible under scanning electron microscope, and what you see there is again similar lines, but these are not beach marks. So you will see these lines, and these lines, each of these lines are representative of one cycle of loading. And we will understand what this one cycle of loading is. So each cycle of loading is distinguished by each of these lines, and this feature which is visible and this feature is very small, so probably in the range of micrometers, and so a few microns or something. So these features are different from beach marks because these are microscopic features, and these are called striations. Beach marks are not representative of each cycle. So here these lines do not represent one cycle of loading, but in striations they represent, so each line represents one cycle of loading. Okay, so now as we understand that fatigue is caused by to and fro kind of oscillatory kind of loading or cyclic loading. So for instance, you have a beam like this, and then you bend it with your hands or by some machine. You bend it in such a way, and so this was your initial position, and then you bend it again in this way. Okay, so and you keep on doing this. So what are you doing is that you are applying tension on the outer fiber and you are applying compression on the inner fiber. When I say fiber, I mean the component. So if you imagine this whole beam to be layers of material, then so if you imagine that this beam is made up of several layers, then the upper layer can be assumed as one fiber and the lower layer can be assumed as a fiber. So fiber, you can imagine it to be a unit in thickness direction having the same length of the beam. So what is happening is that on the inner fiber or on the lower fiber in this case, you are applying compression, right? You see that the fiber is getting compressed. On the upper part you see that it is getting expanded. So from the mean position, when you do this, you are applying a tension on the upper fiber, and when you do this, you are applying compression on the upper fiber and tension on the lower fiber, right? So what actually are you, and if you keep on doing this to the same extent, so let's say you bend it so that the middle position goes up by 5 millimeters and then down also by 5 millimeters, right? So what is happening is that you are applying tension on the outer fiber. So now let us assume only the outer fiber. So what is happening at the outer fiber if we plot stress, for instance, on the outer fiber? So in the first part of the cycle, it is going in tension, okay, and so the middle part, the upper part of the upper fiber and the middle point of that upper fiber, let's talk about that. So at that point, what is happening is it starts from 0. There is no stress in this step number 1. Step number 2, you are applying, you are actually bending it, because of which a tensile stress will be created on the middle point of the upper fiber, okay, and you have not instantly gone to this 5 millimeter of bending, right? So you must have gone through several values of it. So the stress has increased and it reaches the maximum when you are at 5 mm. So it goes to a maximum value. From that, you are now coming to third step, where you are going 5 mm down. So how will you go 5 mm down? You will come to this position again and then you will go back, right? So before going here, it must touch 0 again. So it goes to 0, and then you apply a compression which we show as negative on this sigma axis, right? So I apply a negative and then you again bend it back up and down and up and so on and so forth. So this is how the stresses are moving, stresses are appearing at this point, right? If I have to plot what is happening at the middle point of the lower fiber here, so in the second step I am applying a compression there, right? So that will be going something like this. Okay, so in this experiment, if I do something like this to a beam, I am actually creating damage at two locations, on the upper location and lower location, to a maximum value. Of course, the stresses will be having a gradient from surface to the center, right? So from center to the upper surface, things will be going in tension in second step, and from center to the lower surface, things will be going in compression in the second step, and opposite will be happening in the third step. Okay, so here, and this we have seen in torsion also, that the shear stress actually has a gradient from surface to center. So that will be happening in the beam in any ways, because it is a solid cylinder and the stresses are changing from surface to center. So it's not just a wire where we can ignore the gradient of the stress. So we are creating damage at every point of this beam, but from the center downwards the behavior is exactly opposite of what is happening from the center to the upper surface. And that is not important at this point of time. What is important is that we are applying a cyclic loading. So the stress is going to a maximum, then it is reaching a minimum, and that behavior is being repeated over and over again. So this becomes my one cycle of loading, right? And I'm repeating that cycle over and over again. And in each of these cycles, I'm creating some amount of damage in the system. So before we go there, this is what fatigue is. So a cyclic loading is this. Okay, so this is one cycle. So from O to it goes to maximum at A, reaches 0 at B again, comes to minima at C, and ends at D, the one cycle. So the whole cycle is from O to D following this path. Okay, and this is true for this point. So this is a very smooth kind of cycle what we are doing, and this example is very relevant because in order to break few things at home, we do this thing. We try to break it with our hands by giving it a cyclic loading, and they usually break very easily, and that's why we do it, because and that is an important thing of fatigue, because if you have cyclic loading involved in any of your component, then what is happening is the material is going to fail very easily, right? Because that's why we use this effect to break things deliberately. So we know that if you apply a cyclic loading, then the things are going to break very easily. Okay, so the harm of this kind of deformation is that if a component is being used somewhere where you have cyclic loading applied on that, then the failure chances of that component is high, because you know that they're going to break very easily. Okay, so what happens is material gets exhausted in this cyclic loading to and fro. So tensile compression, or a high stress, a low stress, high stress, a low stress. So that kind of cycle makes the material tired, and it fails because of that, and that's why it is called fatigue of material. Okay, so this is a very simple kind of loading, and in this kind of loading we will define some of the terms which is used in defining fatigue kind of loading. So the maximum value of stress, what it goes, is called the amplitude of stress, and that is given by the difference between sigma max and sigma minimum. Okay, so this minus that will be giving me the value of the amplitude of the whole thing. Okay, and this is usually so this is sigma A, which is the amplitude of the stress, and the amplitude of the stress is defined by the difference between maxima and minima divided by 2. So sigma A, which is amplitude of the stress, is sigma max minus sigma min. And this, don't get confused with the principal stresses what we learned in our monotonic loading. Sigma max is essentially in cyclic loading the maximum amount of stress you are applying on the component. Minimum stress you are applying on the component will be sigma minimum, right? And half of that will be your amplitude. So this amount is the amplitude. Okay, then of course we have mean stress. This is not the mean stress what we learned in the stress tensor thing. This is a different mean stress in fatigue loading, and in fatigue mean stress is the average of sigma max and sigma minimum. Okay, so the mean stress in this case is 0. Okay, so sigma max plus sigma mean divided by 2 is somewhere here, which is 0, because in this case sigma max is equal to sigma mean, because the material is same and we are going 5 mm up and 5 mm down. So we are going up and down by the same amount. So the stress will be induced in the system by the same amount. One will be in tension, another will be in compression. That's it. Okay, so that is sigma min. Then the ratio of sigma minimum and sigma maximum is defined as R. There is no name for this. It's just called the R ratio, and it defines this ratio. Okay, and there is another term which is called amplitude ratio, but that is not very important in fatigue loading. So this is not used a lot in understanding the fatigue loading, but nevertheless this is a ratio which is used in literature. So amplitude ratio is the ratio of the amplitude of the stress divided by the mean stress. So where are you in comparison to how much amplitude you are applying? And this will be clear when we see a different kind of loading condition. So this is a very simple loading condition from which we understand these variables which are important for defining and also understanding fatigue loading. But what can happen is you can have a different kind of loading in the system. Okay, so first is that you do not have to have a tension compression cycle. You can have a completely tension cycle, or you can also have a compression cycle. Okay, but compressive stresses are not that damaging in comparison to tensile stresses. So if I have a tensile cyclic loading, then that may look like this. Okay, so this is 0. This line represents the x-axis where the value of y is 0. That means there is no stress here. So what am I doing? So if I have to plot the mean value, if I have to do the sigma mean, then sigma max plus sigma mean divided by 2. So sigma mean will be somewhere here, right? So this is my sigma max, this is my sigma min, and let's say this value is 5 megapascal, and so this is 5 megapascal. So so this may be 10 and then we can have 5 more, so maybe 15. So let us say that this is 15 megapascal. So our mean value is 15 plus 5 divided by 2, which will be 10 megapascal. So that will be my mean value, right? And the amplitude you can see is 5 megapascal. So in this case, my sigma A is 5 megapascal, and that you can calculate. So that will be 15 minus 5, which is 10 divided by 2 is 5. So that is my sigma A. So amplitude of the stress. So what is happening here is that in this case I am not going in compression, but I am going to a higher value of tensile stress, and then I am coming back to lower value of tensile stress, then I am going to a higher value of tensile stress again, and so on and so forth. So I am having a cyclic loading in tension always. So the material is always in tension. It is at higher tension sometimes and lower tension sometimes. Okay, so this kind of cycle can also exist, but even then this is a simple cycle. This we can do in laboratories and understand how the material will perform in certain condition, and these kind of cycles are used for. So in this case, what will be my R ratio? R ratio will be sigma minimum is 5 and sigma maximum is 15, right? So that is 1 by 3. Okay, so amplitude ratio, if I have to find out how much that will be, sigma A divided by sigma mean. Sigma A is 5, sigma mean is 10, so this is 1 by 2. Okay, so what does it say? That the amplitude, so the mean stress is twice of the amplitude, right? So the average value of the stress which is being felt by the material is double of the amplitude of the material. So by the amount you are varying the stress in the material, the average stress is double of that. This is what it means. Okay, but this is, you may say that this is very clear from the diagram, but some cyclic loading, so these two examples are very simple examples of cyclic loading, but in some cyclic loadings you can have a different scenario. So that we will see in the next page. So these are a simple situation which we can do in the laboratory, and we can understand, and those kind of cyclic loadings are applied for understanding the material's performance. But in reality, those kind of loadings will never be applied in a material. So what happens in true nature of a component is that you can have a cycle which looks like this. Okay, it may look like the cardiogram or something, but it happens in reality. So the stress will not increase smoothly. It will go to a maximum value, then will sharply come back to 0, then it will go to, so this cannot happen. Okay, and so what I'm trying to say here is that the stress cycle can be very irregular, and in this case those parameters which we defined are not going to be very clear. So this is my sigma max and sigma min in the first cycle, but you see that sigma max and sigma min has changed in the second cycle, changed in the third cycle, and it is changing always. Okay, so my sigma A value is also changing with the number of cycles, and then my sigma mean value is also changing. So what is my sigma mean in this case? So if I just consider 1, 2, 3 and 4, so one cycle is here, another cycle is, so one cycle will end here, and then another cycle will end here, and then another cycle will end here. 3 cycles, and then 4th cycle. So let us consider only 4 cycles of loading. Okay, so what is happening to my mean stress is actually, so my mean stress in the first cycle is where? It's somewhere. So we can imagine that it will be 0, right? and then the mean has increased because my sigma max is there but sigma minimum has decreased, so my mean stress has suddenly gone up at this point of time, right? And then again here it has, so it will be sigma mean will be there till this cycle, and then it has decreased because both sigma max and sigma mean value have decreased, so suddenly it will be somewhere here, and then again it has decreased to some value close to 0. So you see that sigma mean is itself having a variation, and sigma amplitude is also having a variation. That is also very clear, but this will be the real scenario, and analyzing this will be very hard. Okay, so the theories to analyze such behavior comes from those basic smooth sinusoidal curves by which we generate the material behavior parameters or fatigue parameters. So what we understood in the last page is that you can have a variation in stress, but you can also have a variation in strain. Okay, and similarly you can have maximum strain, minimum strain, and average value of strain, but usually the reports, the values are given in the form of stress and not strain, but you can have two types of testing of fatigue. So when you do the testing of fatigue, you can actually define that the stress should go to this value and come back to that value, or you can do it in a strain controlled mode. So there are two types of modes available. You can have strain controlled fatigue testing, or you can have stress controlled fatigue testing. So what you do is you simply define, in this case you define what is your amplitude of strain, and then you define the mean value of strain. And similarly in this case you define the amplitude, and you define, so amplitude is delta sigma. Usually it is described in terms of delta sigma divided by 2 will be your amplitude, but in literature you will also find that people plot the data with respect to delta sigma. So delta sigma basically will be as it looks like sigma max minus sigma mean. Okay, so the testing is usually performed by making or defining the strain, or you can do it by defining the stress. So you can have a cycle of stress or you can have a cycle of strain. It is possible both ways. So the testing of fatigue is performed similar to what you have in tension test. So the specimen is usually looks the same. So you have threads because to fix the specimen in the material, and then you have a dog bone kind of specimen with a parallel gauge length, and then you have the grep section, and then you have threads again. Okay, so you put the upper part in the machine, put the lower part in the machine. So this is your gauge length again, and then you can measure the diameter also. The difference between tensile test specimen and fatigue test specimen is that before doing the test you polish the surface of the specimen to mirror polishing level, usually for metallic materials, because the reason why you have to do this is because in fatigue surface is very important. Okay, so, and we will see why. The mechanism, the damage which happens in the fatigue usually starts from the surface. So but before going there we have to understand something which comes from the fatigue testing. So what you do is you mirror polish the surface of the specimen, then you put it in the machine like we did in the tensile testing, and only difference is that in tensile test we had stress strain curve. So you apply displacement, and as a result you get the force from the machine. From that force you convert that force to stress and convert the displacement to strain, and you get this kind of behavior, right, in tensile testing. What happens in fatigue is that you apply a cyclic loading, right? So what you do is you apply, let's say, so we'll have to draw here. So let's say you apply 5 mm, you're going up, and 5 mm you're going down. So this is stress, this is a strain. So in this case what will happen is, again, you're going linear and then non-linear, right? And this has happened until you reach the strain value. So let's say you have defined that I will go to a maximum strain of maximum stress of 15 megapascal was the example in the last page, and then 5 megapascal in the tensile field, right? So here, and let's say the yield strength of the material is 10 megapascal, okay? Okay, so 10 megapascal is the yield strength. So let's say this is 10 megapascal, and then it goes to 15, which is there, okay? So this is 15, this is 10, and now you have to go in the, so you have to go to the 10 megapascal again, right? So you will come back, you will unload the material to this point. So when you unload, it will follow the elastic modulus. So it will come like this, right? But then the minimum value of stress is this, and then you will repeat the cycle again, right? So then you will again increase the stress to 15. So it will go like this, and then it will come like this. It will go like this, it will come like this, it will go like this, and so on and so on. So this is how your cyclic stress strain will look like. But this was a complicated scenario. So if you apply, let's say, for steel, let us say that the yield strength of steel is 200 megapascal, and we are giving a maximum stress of, let's say, 400 megapascal, and we are going back in compression. So our sigma min is minus 400 megapascal, okay? So this will be something like this on a stress axis. So the same amount, what we are going in maximum, we are going by the same amount in minimum in opposite direction. So in that case, what will happen is that your stress will go